Hello, everyone. Welcome to this webinar. My name is Jonathan GULA. I am an associate professor in physical oceanography at the University of Brest in France. And I'm going to talk today about the Gulf Stream. So this presentation is the second one of two presentations. The first one was given by Magdalena Andres and was focused on observation efforts. So here I'm going to highlight some of the modeling efforts for the Gulf Stream, and in particular, our observations from global and regional coastal systems can be used to help improve models. So this is by no means a comprehensive review of on the topic of the Gulf Stream modeling. This is a pretty vast topic, and so I'm just gonna try to present some elements to fit the discussion and highlight some links between the different types of modeling and the observations. So as a brief outline, I'm going to present basic thing about the Gulf Stream, but especially if you've seen the first presentation, you are already familiar with it. Then I'm going to talk about different aspects of modeling for the Gulf Stream, different types of models that are used at different time and spatial scales. Highlight a few issues and limitations of these models. So then I'm going to discuss in more details what is currently done in terms of confrontation between model and observations. I will focus in particular on the problem of the validation of the models for different types of dynamical regimes and which type of data are available. I will also briefly discuss aspects of data simulations and forecasting, but these are very important issues. But as this is not my area of expertise, I will leave most of it for the upcoming discussion. So the Gulf Stream is a western monary current, transports heat, salt, nutrient-rich waters poleward. You can see an animation of sea surface temperature from a North Atlantic coupled model here. So the Gulf Stream plays a major role in climate, North Atlantic biogeochemistry, for the uptake of atmospheric CO2, supply of nutrients, oxygen budgets, also impacts the atmosphere. Dynamically, it's also a very interesting place because that's where a large part of the eddy kinetic energy of the ocean is dissipated. So it acts as a graveyard for all the mesoscale eddies that are generated in the subtropical gyre, and is regions where a lot of small-scale processes will have to dissipate energy and also generate mixing, especially along the slope and where we have important topographic features. So the upstream part of the Gulf Stream flowing along the continental slope, so between the Florida Strait and Cape Hatteras, is also routinely a region where mesoscale, so tens of kilometers wide structures, and submesoscale, so kilometer scale structure, are observed. These structures play an important role for the cross-shelf exchange processes, so between shelf water and the stream, with important dynamical, ecological, and biological implications. If you look at the Gulf Stream more closely after it's separated from Cape Hatteras, you'll also see a lot of meanders, Gulf Stream rings, and also submesoscale structures in the forms of fronts, filaments, and eddies with spatial scales on the orders of kilometers. So as seen on the ocean color image visible here. So the mesoscale structures have been studied for some time. They are known to generate important horizontal turbulent fluxes with impact on the mean currents and properties. The submesoscale also have an important impact. So for air-sea exchanges, lateral mixing, for example, across the Gulf Stream North Wall front. They also generate vertical fluxes between the surface and the interior, with the implication for biogeochemical budgets, the formation of mud waters, and other type of implications like this. So there are very schematically different type of models that can be used to model the Gulf Stream. It starts from the oceanic components of climate models. So typically the CEMIP models, which are used in the context of IPCC reports. These are models with typical resolutions of tens of kilometers, so usually unable to resolve the mesoscale eddies. So we talk about eddying ocean models for the 1 So typically with horizontal grid scales on the order of 10 kilometers, which are able to resolve bulk instability and the duration of mesoscale eddies and impact on the flow. So these are the models that are commonly used to study the ocean circulation with numerous applications in operational oceanography. Over the past few years, we have also seen the development of global or at least basin scale models, so able to reach the upper range of submesoscale, so with resolution on the order of a kilometer, that we call submesoscale permitting. And finally, we have limited extension domains, so regional models, which can be submesoscale permitting as well, or submesoscale resolving, when we go to hundreds of meters or less. And these are very useful for regional applications, process studies, and a wide range of applications. So the Gulf Stream is notoriously difficult to model, especially for climate scale models. A well-known issue present in many of these models is the overshooting of the Gulf Stream. So for example, in other words, the Gulf Stream doesn't separate where it should at Cape Hatteras, but it just follows the continental slope and penetrates too far north. This is very common in models, as you can see on all these panels showing mean SST bias in 1 degree experiments. So as it separates too far north, it induces a strong positive SST anomaly north, and negative south also have implications for the North Atlantic current downstream. And so these strong temperature anomalies generate systematic RC fluxes biases with implication for the atmosphere, weather, precipitation over Europe, so many problems in climate models. This problem is often solved by increasing the resolution, diminishing the effective viscosity to get a more inertial Gulf Stream. So then usually the separation becomes more realistic. You can see an example of that on the figure. You have an overshooting model. You see the contours in black here on the upper panel, compared to the observations in green, so how it should be. So this is strongly improved when we get to eddying models with 6 and 10 kilometers here. However, you can see an interesting fact that in this case, we get a small bias in the form of a permanent meander just after separation here, which is common in models where we have a bit too strong eddy activity. And this can be resolved, for example, by removing energy. So in this case, it was resolved by adding atmospheric coupling or just considering relative winds in an ocean force model. Relative winds meaning we take the difference between atmospheric winds and ocean currents to compute the stress at the surface. This has an eddy killing effect, remove 20 to 30% of the eddy kinetic energy in this region, and give very realistic results, at least for this configuration. So if you compare the red and black curves there. Increasing the resolution further, and also eventually adding high frequency variability, which is what is done in most models of this type, also has consequences on the Gulf Stream meandering and variability. So typically, resolving submesoscale may induce upscale energy transfer and energize further mesoscale eddies in some region. In others, you can also have internal waves acting to extract energy from the eddies. So you are adding new pathways for energy and modifies the mean structure of the flow in many cases. So there is a strong effort currently to intercompare the different type of models of this type. You can see examples here showing a snapshot of vorticity in the Gulf Stream region for 6 of these models. The interesting thing is that they are all using different type of numerical options: vertical coordinate, subgrid scale turbulence parameterization, advective scheme, etc. So it is very useful to compare them and see differences in the differences in the setup translated to differences in the statistical properties of the flow. Some works have already shown that for some of these models, at least the increase in resolution was leading to a more realistic structure of the Gulf Stream. You can see an example here of ICOM simulations going from a 12th of a degree to 50th of a degree, where the variability is stronger as expected, and it leads to a more realistic eastward penetration of the Gulf Stream, and also more realistic vertical penetration of EKE, and more realistic vertical structure of the current. So then you can also go further by using sub-mesoscale resolving models. So usually over much more limited regions and for smaller periods, typically months. So this can be done by nesting high resolution models into lower resolution ones, Bayesian scale solutions, or analysis. You see an example here of a vorticity snapshot of the Gulf Stream after separation, with even more intense sub-mesoscale fronts, filaments, and associated vertical velocities. And it doesn't really show signs of convergence yet, so we know there is still work to properly model this kind of scales. There are also important small-scale processes happening at the bottom of the ocean, so especially where the current interacts with the topography. You can see an animation here of the Gulf Stream flowing along the slope. The colors are showing relative vorticity, and the surface correspond to one isopycnol in the model. It shows in particular a turbulent wake on the lee side of the Charleston bump, which is a gray area here, outcropping the isopycnol at this location. Generation of more sub-mesoscale eddies or mesoscale eddies in the flow. So you see that models are trying to get more and more realistic. So at least in terms of processes included in the physics of the model, and they're going to finer and finer resolution. But of course, these models are far from perfect by definition, and they need to be constantly confronted to observations. First, to be validated, to be sure that the physics, numerics are doing a reasonable job at least. And then eventually observations can also be used for data assimilation, so to constrain the model, or even to construct parameterizations for processes that are not resolved by the models. So what you validate in the model really depends on the objectives of the model and the spatial and timescales that are targeted. So it goes from the mean structure of the currents, mesoscale variability, sub-mesoscale properties, high frequency activity, so what happens related to the internal waves and tides, and even the small scale turbulence. So in particular, what's happening in the bottom boundary layer or in the surface layer and related to RC turbulent fluxes. So basically the question is which type of observation can we put in front of that? One of the most useful data sets is, of course, altimetry. If you are interested in mesoscale and larger, you want to monitor the path of the Gulf Stream, like in the figure here. This is how it is usually done. Unfortunately, the effective resolution of altimetry is on the order of almost 100 kilometers, let's say, and it's also not always variable near the coast. So, for example, you cannot get the full amplitude of SSH gradients for the Gulf Stream when it flows along the slope here. So this type of data can also be combined with drifters. So there's a growing global database of drifters that can be used to help mitigate this kind of issues. Thinking about mesoscale variability, the same data can be used. So maps of SSH variability or EKE derived from that is very useful to compare the different type of models and assess their realisms. So of course, altimetry correspond to scales which are on the order of 100 kilometers, time periods on the order of 5 to 10 days. And models usually have to be smoothed out to get to the same spatial and temporal resolution to make up for a fair comparison between the two. You can see, for example, what happens here if you compute spectra for SSH variability in the model, you get something much stronger than in observation. But if you smooth out using a 10 days period and a bandpass filter of about 150 kilometers here, you get to something which is pretty similar. So hopefully the new satellites, like the SWOT satellite, will help provide information at these smaller scales, even if, of course, the time sampling will still be an issue. If you are interested in what's happening below the surface, it's even more difficult to check the realism of the model. So the vertical structure of the currents, we don't have a lot of data to compare it with. If you have seen the previous talk by Magdalena Andres, you've seen that there are a few repeated sections, like the one in the Florida current here. There are moving lines like line W, and these are typical examples of what you can compare between model here and observations. But unfortunately, there is not a lot of data between these lines in terms of repeated sections to get the mean structure of the current. Despite the strong changes happening in the structure and variability of the Gaussian between these two sections. As a quick example, for example, if you just use all the available TS data from the World Ocean database, you can construct a mean temperature profile here. So if you use interpolated data, of course, it's a problem because the gradient is smoothed out. But if you just bin all the available data, so more than 50 years of data, you start to get something decent here. And it's possible in this location only because the current is mostly flowing along the slope, not meandering a lot. Because if you do the same thing after separation, it will just be completely smoothed out because of the meandering of the current. So now, if you also want to quantify the mesoscale variability in the interior below the surface, it's possible at least down to 2000 meters. For example, you can use observation from the Argo floats, compute diagnostics such as eddy available potential energy. This is something related to the vertical displacement of isopycnals and comparisons between models and then this Argo dataset are very useful to provide some vertical structure of the mesoscale variability and help characterize different types of regimes. More recently, data from the GUIDOS program have also been compiled to come up with mean and the eddy kinetic energy over the first 1000 meters in this region where the Gaussian is flowing along the slope. So this is a very useful dataset that will can be used to compare with models. So when it comes to even smaller scales than that, the sub-mesoscales, it becomes even more difficult to find data with enough spatial and time resolution to come up with useful statistics that can be compared between models and observations. So SST ocean core images are showing a lot of nice features at the surface at small scales, but they cannot be used to infer the dynamics, the velocities, for example. So our knowledge comes mostly from dedicated multi-instruments experiments, such as the LatMix one, whose design is shown here. So this type of experiments typically use several ships, a lot of instruments, and focus on a specific region. Here's the north wall of the Gulf Stream in order to provide a lot of high-resolution simulations at the same place. So, and one of the very interesting experiments in terms of model validation that came up of that is an experiment where two ships were used in parallel, as you can see it, in order to provide 2D velocity gradients, so that you can get statistics on vorticity, divergence, and strain distributions in the flow. So if you compare the same statistic from the model that you see on the top panel, from these observations here, you can see that you get fairly distributions in fairly good agreement. So histograms are observations, the red curves are the model. So this is one example of very successful comparison at this scales, but it is really one of a kind. So if we go to deeper below the surface, as you can imagine, it's even more difficult to get observation with fine enough spatial coverage and time sampling. You can get glider sections in the upper 1000 meters that provide kind of snapshots of the pretty small scale structures. For example, here you see a model on the panel showing the formation of small scale eddies. So we can make qualitative comparisons with gliders because we see the same type of structures. not exactly the same at the same place, but just the same class of structures. We can find the same things, for example, in opportunistic seismic measurements, which shows a fine scale vertical gradients in temperature mostly. But this is really qualitative, and it's difficult to get something more quantitative when you talk about this type of dynamics and structures. So especially as we know that close to topography, a lot of important mixing processes are happening. So one way to map this, for example, and gliders have been used to do that, were to measure the thickness of the bottom boundary layer with the gliders. This can provide a map that you can see here with the mean and the variability of this bottom boundary layer depth. And this is, again, another diagnostics that we can compare to model. So in this case, a very high resolution model of the region is doing fairly good in terms of producing that, but it's difficult to go further in terms of comparisons and validation for this aspect. So especially the mixing itself is very difficult to quantify and to observe. And we know that it is an area where models have flaws, and it's very difficult to check how they're doing and try to improve these aspects. If we look at specific microstructure measurements, so to measure the small scale dissipation and mixing, we don't have such a large number of direct measurements. Globally, we don't have a lot of measurements, and the Gulf Stream, despite its importance, is no exception to that. We have a few microstructure measurements in the Florida Strait. Again, you see some example here on the right. We also have some data along this section. This is the Hollander section, I think. But these are not microstructure measurements, but data which are inferred from CTD and ADCP. And so we need to better understand what's going on, especially between the Florida Strait and the section here, which is downstream of separation. So, for example, recent work has highlighted that some of the mixing in the Florida Strait, for example, the band of high mixing you can see on the western slope here, can be reproduced in idealized and realistic models when we take into account tropical storms, generation of inertial waves. This inertial wave propagates, in the flow, can be reflected on the western, the eastern slope, and then they can focus into the critical layers that are formed here, where the isopeak nodes are more or less following the continental slope, and they are trapped here and generate this strong mixing. And there are presumably a lot of other type of processes, small scale instabilities, Lee waves, for example, especially at the Charleston belt, that are acting to generate mixing and induce water mass transformations. But we don't know much about this from observations, and it's difficult to evaluate models on these aspects. So when it comes to data assimilation, everything becomes even more challenging. So we have barely enough to compute long-time statistics on sub-mesoscale processes. So getting enough 3D data and resolving the time and spatial scales involved is even more complicated. There is a nice example shown here of high-resolution modeling and data assimilation on the Mid-Atlantic Bight at the location of the Pioneer Array, so where a lot of data are available. And it manages to reproduce fairly well the circulation even at close to the sub-mesoscales. And it has been shown that, in particular, the velocity data from the Pioneer Array played a critical role to reduce uncertainties in the reproduction of the circulation. So this doesn't come as a surprise, but 3D data with high enough resolution, in particular velocities, are needed to do that. But it's again reinforcing the point that we need to get as many of this data as possible to be able, one, to evaluate the models, and also to perform a data simulation at this case. So in conclusion, I will just stress again the importance of ocean observing networks for improving ocean circulation models. These sustained observations from the satellites and the in situ networks are really critical to routinely assess the skills and limitation of the circulation models over time scales ranging from hours to decades. So I will just repeat some of the recommendations made in the first talk, especially pertaining to the need for more frequent direct measurements of velocities with high enough resolution in different places of the Gulf Stream. Ideally, also experiments designed to measure velocity and tracer gradients at meso and sub-meso scales, like moving arrays, swarm of autonomous instruments, will be very, very useful to better understand and evaluate the meso-sub-meso scale properties of turbulence in the models. I will also stress again the need to measure what's happening in the deep ocean below 2,000 meters, where many things are happening, but models are really loosely tested and constrained. And finally, direct measurements of the small-scale turbulence will be also instrumental to evaluate and improve the representation of mixing processes in models. And the Gulf Stream would be a particularly fine place to do that because we know a lot of things are happening at all scales, and they can have huge impact on larger scales and climate-related issues. So thank you for your attention. I think this presentation has been pretty long already. So thank you again, and looking forward to the coming discussion. Bye.